Assalamu alaikum dear students, we're back with another video lesson. In the previous video lesson we were talking about Newton's second law in rotational motion. We said the net torque is equal to moment of inertia times angular acceleration. We said considering an object rotating counterclockwise, the net torque will be positive if the angular acceleration is positive, which means or in the case of speeding up we can say. But if the object is slowing down while the object is rotating counterclockwise, then we can say the net torque is going to be negative because now angular acceleration is going to be negative. Assalamu alaikum dear students, we're back with another video lesson. In the previous video lesson we were talking about Newton's second law in rotational motion. We said the net torque is equal to moment of inertia times angular acceleration. The net torque can be positive or negative. We said it is positive considering the object rotating counterclockwise if the object's angular acceleration is positive. In other words, if the object is speeding up while it is rotating counterclockwise, then the net torque is positive. But if the object is slowing down while it is rotating counterclockwise, then the net torque is negative. Which means that omega final it is going to be smaller than omega initial. And then after that, we talked about the unit of net torque. We said it is or the SI unit for net torque, it is Newton meter. And then we solved a few questions. We ended up right at this question here. Question 38, the question says, a 12 kilogram mass is attached to a cord that is wrapped around a wheel with a radius of 10 centimeter, as shown in the figure. The good news regarding this question is the diagram will be given. And by the way, this has been in Wizari very recently. It says the acceleration of the mass down the frictionless incline is measured to be 2 meters per second squared. That is tangential acceleration. Assuming the axle of the wheel to be frictionless, determine the force in the rope here. All right, so let's answer each answer the requirement that is mentioned here. The first thing to start with, how about we write the information that is given and see what is unknown, and then after that we can start working on this. Okay, now the first thing that is given, it says a 12 kilogram mass attached to a cord in here. So you can see from the diagram that is a 12 kilogram mass attached to a cord. Or you can say attached to a rope here, and then this rope is it is moving or rotating on a frictionless wheel here. The radius of the wheel is 10 centimeter. The acceleration of the mass down the incline is 2 meters per second squared. This incline makes 37 degrees angle with a horizontal. The question says, what is the force in the rope here? That would be F tangent, you can say. Okay, so let's begin with this one here. How about we just do the whole thing from the beginning here. So here's the mass. Okay, here's the incline. This mass is connected to a rope here. This rope is connected to a wheel. This wheel is obviously rotating. Just write it here. Okay, here's a cord. This mass is 12 kilogram. This is 37. The acceleration of the mass down the incline is translational acceleration, by the way. It is 2 meters per second squared. Of course, there is F tension downward here. The question says, find this F tension here. How do you find F tension here? Now, first of all, you might wonder, what equation do I need to use in here? Do you remember we said there are 3 equations of Newton that we can use them here? So the first one was for translational. We said F net was equal to mass times acceleration. That was for translational equilibrium, yes? And the second we said for circular, F centripetal mass times centripetal acceleration. The third one was for rotational, where the net torque was equal to moment of inertia times angular acceleration. Which one of these equations do you think we're supposed to, or we should start using? Clearly, that is the first one. Why? Because the object is moving in a straight line. Isn't that translational motion? Yeah, so here's the first equation that we're going to use. But then there is one thing you need to know. why is the object sliding or moving downward? That is because, or the effect of gravitational acceleration here. So in other words, we can say that this mass, of course, there is Fg, which is straight downward here, but then this Fg will now be analyzed to two components. One of them, it is parallel to the surface of the incline, which is going to be Fg sine theta. The other side here, it is going to be Fg cosine theta. And this is, you can say Fg, but instead of Fg, we're given the mass. And for Fg, we can say mg times that. But remember this, there are two forces in here. One of them, it is the gravitational component, which is downward. And then F tangent is upward. If we're going to use Newton's second law of motion here, we'll say F, remember, this is the net force in here. And when we say net, that is clearly the total, which you already know that. So F net, it is equal to mass times acceleration here. But once again, this F net, how do you find the net force? We'll say all the forces added together, this is how we can find the net force. But if one of them is in opposite direction, then we could say minus or subtract from the other one. So, but here's another question. I have two forces here, Fg sine theta and F tangent here. Which one should I write first? Okay, that is a good question, because the one that you write first, of course, it might change the course of the solution here or the answer at this point. So let me give you an idea. Didn't we say, like in the other session, that acceleration and force will always be in the same direction, or the acceleration will always be in the direction of the net force? Let me correct that perhaps. Okay, so because the acceleration is moving downward and this positive, which that means this must be bigger than the other one. What would have happened if this was bigger? Then this acceleration would have been, if the object was kept or still moving downward, it would have been negative here, or the object would have moved upward. So this is how we would know if F tangent is bigger. But at this point, because the acceleration is downward and it is positive, which means that this component of gravitational force must be bigger than this one here. This is how we know which one to write first. So in this case, Fg sine theta minus F tangent, because these are in opposite direction, I can say plus minus, makes no difference. It is equal to mass times acceleration. Now, of course, some of you might wonder, why are we using Fg sine theta? Why it is not cosine theta? Well, that is another story. So now I believe I can erase this one. Let me tell you a little bit about this one here. First of all, let me tell you, by the way, these two, I forgot to mention that these two angles will always be the same no matter what. So if this is 37, this is 37 as well. How do I know these are the same angle? Let me tell you this. This is the mass, consider this is the mass. And if I do this one here, this angle is 37, correct? If we draw just the mass, like mass or gravitational force is always perpendicular downward, always. And then this gravitational force would analyze to two components. One of them is, let's change this color. One of them, it is parallel to this, you can say the other one is perpendicular to the surface in here. And you do know that if this is 37, this is a right angle. So what do you think is this angle here? All right, we can say 90 plus. If this doesn't these angles make a right angle triangle here? So this is 90, this is 37. What do you think this angle is? Okay, so let's find out. We know that the total is 180, yes? The total is 180. Now, one of them is 90 already. So 37 plus what equals to 90? Or you can say 90 minus 37. In other words, this angle is 53. But watch this. Isn't this also, you have to be careful here, isn't this also a right angle triangle? Sorry, not forget the triangle here. Isn't this a right angle here? Yes, it is. If that is the case, if this is 53, what do you think this angle is? Isn't that 37? Because both of them together must add up to 90 here. So 57 plus 53 plus 37, that equals to 90. So now, since we know this one, so whenever you're given angles with the horizontal, don't forget now, from this point on, whatever this angle is, immediately this angle will always be the same. That is first. Now, after we're done with this, the second point is this. In grade 11, we've learned that if we have a force, whatever the force is, we said whichever the side with the angle, that would take cosine. So in this case, let's say for x-axis, this point here, let's avoid using x and y. For this side here, it's going to be f cosine. For the other side, it's going to be f sine theta. If the angle were here, this two thing would switch. Now, regarding this one, going back to this, you can see that this component that is with the angle, like it doesn't matter which side is the angle with. Like it's not always x is cosine and y is sine. No, it depends on which side is the angle with here. So the angle is with this side here. So this side is going to become fg cosine, and this side now it is going to become fg sine theta here. So these are what we have, and the angle, you know that fg, that'll be mg here, sine theta, that is going to be sine 37 there. So instead of fg, we're given the mass, don't forget. So instead of fg, I'll write mg, sine 37, because that is the angle, minus f tangent, it is equal to mass times acceleration. One more time, the mass is 12 kilogram times 9.81, right? And then times sine 37, minus, these are, the whole thing is fg sine theta, minus f tangent, let's just write f tangent, minus f tangent, that is equal to the mass again, 12 times the acceleration, which is 2. Okay, now let's multiply this 2 and then find this one here. 12 times 9.81 times sine 37. The answer is going to be 70.85 by rounding. 70.85 minus f tangent, it is equal to 24. Now, take f tangent to the other side and then bring 24 in here. 70 minus 0.85 minus 24, it is equal to f tangent here. Okay, so what is f tangent equal to? 70.85 minus 24, it is equal to 46.85. So we can say f tangent is equal to 46.85. And of course, by rounding, you can make it 47 as well, just in case, and that is in Newton because it is tangent at this point here. That is the first part, or the first requirement here. Find f tangent in the rope, and we just did it here. Now the second part of the question, right? Second part of the question says find the moment of inertia of the wheel here. How do you find the moment of inertia of this wheel or this pulley that is rotating here? So if this is rotating, watch this. This is the axis of rotation. The radius is 10 centimeter. If you convert this one to meter, that would be 0.1 meter. You agree, right? Okay, that is this. And then this rope is trying to apply a force on this one here. So we can say F tangent, which we just found, it was 46.85, we can say. We can round it up to 47 if you want to. Okay, so how do you find moment of inertia for this one here? Well, it's easy enough, I guess, right? So for the wheel here, there is one more thing, let me tell you. For the moment of inertia for this wheel, if I had the mass and the radius, I could have found the moment of inertia for this wheel. I could have used a disk, for example, or the question must have clarified a little bit more here. So we could have just said 1/2 times mass times radius squared. But the problem is I have the radius, but I don't have the mass, right? So I cannot use this equation. If I don't have, I'll have to use the net torque equation. And the net torque equation, it is equal to moment of inertia times angular acceleration, yes? But now for the net torque, we have the force on the radius here. So F times the radius, it is equal to moment of inertia times angular acceleration. But here's another problem. Do I have angular acceleration? No, but I have tangential. How can I find angular acceleration? Wouldn't that be tangential over the radius? Yes. What is the tangential acceleration? It is just 2. What is the radius? The radius is 0.1, so that is going to be 20 radian per second squared here. Okay, now the force that we have just found was 46.85. Let's just use 47 perhaps times the radius, which is 0.1. That is equal to moment of inertia times 20 here. Okay, now can you find the moment of inertia? That is 4.7. Moment of inertia times 20. Both sides divide by 20. Okay, so moment of inertia is equal to 4.7 divided by 20. The answer is going to be 0.235. So we can say moment of inertia, it is 0.235, that is kilogram meter squared. That is the moment of inertia for this, you can say, pulley or whatever that is given here. That is the second requirement. Let's see what is the third requirement. All right, it says moment of inertia of the wheel. We just found it, right? The next thing says find the angular speed of the wheel 2 seconds after. 2 seconds after, watch this. Find the angular speed of the wheel 2 seconds after begins rotating. It says 2 seconds after, so this is delta t, right? Begins rotating, so that means omega initial must be 0 because it says 2 seconds after begins rotating from rest. If not, you could just look at this one here. Starting from rest, that means omega initial, let me just write it here. Omega initial is 0, so find omega final 2 seconds after it started rotating here. We have the tangential acceleration. This is angular speed, so now we have the angular acceleration. We can easily do that one there. Okay, so let's just go ahead and finish the job in here. Okay, so the next thing that we have, that'll be part C, says find omega final. How do you find omega final? Remember, we have the angular the angular acceleration. Can we use one of the 4 equations that we have? Yes, you can also use this equation too. Angular acceleration is equal to omega final minus initial divided by delta t. Yes, we need to find omega final, but we already have this equation already like arranged. Then that'll be the first equation, right? First equation says omega final, omega initial plus angular acceleration delta t. Isn't that right? Omega initial is 0, omega, or you can say angular acceleration is 20, and then after 2 seconds, so we can say omega final after 2 seconds, it is going to be 40 radian per second. 40 radian per second, and that's it. See, it can easily be found. And by the way, these questions can be changed, of course, depending on what is given and what is unknown here at this point. For example, we can, or in a question, they can give you the moment of inertia. They can ask for, let's say, they can ask for the network. And then once you find the network, you can find let's say the frictional, not the frictional, let's say the force that is in the rope, which we call it F tangent here. So it depends on what is given and what is unknown, but always read the question carefully so that you'll never make any mistakes. All right, now there is one more thing actually, okay? If we take this question a little bit further, like if we extend it here, it says what would happen if the acceleration were negative? If the acceleration were negative, that means the object would be slowing down. And it would only slow down if F tangent it is bigger than this component of the gravitational force, which was Fg sine theta. Once again, if the acceleration were -2, for example, what would have happened in this case? You could have used the same equation, said Fg minus, let's just write the angle to Fg sine theta minus Ft, it is equal to, if the acceleration were negative, could have write minus ma, yes? And then at this point, this would have, we would have moved this one to the other side and then bring F ma to this side. So in other words, we can say Fg sine theta minus, plus mass times acceleration, that all equals to F tangent, then you could have found F tangent. There's one more part actually, what would have happened if we, make it even more complicated than this, and that is if we ever, for example, if you want to add the friction into the surface as well, in that case, of course, things would be even more complicated than this. I don't think this question will ever be in Wazari, so I believe I don't have to tell you this. Okay. Now we are at a question actually. This question, or because of this question, I can tell you that a lot of students did not get 100 in the previous Wazari question, you can say, or in last year here. So let me tell you the idea and why they did not get a full mark just because of this question. Sometimes it happens due to a lack of attention, you can say, or not reading the question very carefully, because it's very crucial. All right, first of all, let's underline what is written here. Then after that, we'll solve each part at a time. But the first thing, I need you to underline what I'm doing at this point. It says, 39 says, the combination of the applied force and the frictional force, combination of the applied force and the friction force produce a constant torque of 36 Newton. I need you to underline this for me, and this is the line where most of the students lost 2 marks because of this, for those who did not get 100. Okay, the applied force acts for 6 seconds, during which time the angular speed of the wheel increases from 0 to 12 radian per second. So can I call this one initial and call this one final? Yes. Then the applied force is removed and the wheel comes to a rest. The wheel comes to a rest, that means omega final is 0 now, in another time which is 65 seconds here. Answer the following question. The first thing says, what is the moment of inertia of the wheel? Now, let me tell you this. At any point, if you have 2 omega initial and finals, let's say in a question, it is always best, if it is increasing, decreasing, and then decreasing, and let's say and becoming 0, it is always best to do this. So make sure you do this one, what I'm going to do here. So first of all, let's bring this one here. And let me tell you exactly what you need to do at this point in order to avoid making mistakes. Always try to draw a diagram here. So that is what happens here. An object starting from rest. And then after that, let's just say starting from rest, that means omega initial is 0. And then after that, once that is clearly when the force is applied, the angular speed increases from 0 to 12. So this is omega initial, omega final becomes what? Becomes 12. And then after that, the applied force is removed. If it is going to remove, it is going to decrease from this to 0 here. To what? To 0. Let's get this one back. Let's just fix this one. Okay. So after the force is applied, it is going to slow down here until omega final becomes 0. But let's not forget this. How long does it take? Let's say for this tire, for the okay, acts on during the angular speed of the wheel. How long does it take the wheel to increase from 0 to 12? That is 6 seconds here. So we can say delta t here, it is 6 seconds. And then after that, it is going to slow down. But here's the thing, at what angular speed is going to slow down? It is going to slow down from 12. So can I say this is initial for slowing down? Yes. So for this part, I'll say speeding up. And for this part, I can write slowing down. Slowing down. But how long does it take to slow down? It takes 65 seconds here. All right. And don't forget the net torque, which is 36 Newton. Okay, so what is the first part of the question? What is the moment of inertia? What is the moment of inertia of the wheel? Okay, so let's do this one here. What is the moment of inertia of the wheel? Now, we know that the net torque is equal to moment of inertia times angular acceleration here. The net torque is already given, right? The net torque is 36 Newton meter. And then the moment of inertia, it is unknown here. And the angular acceleration, it is 12 minus 0 divided by 6 seconds, right? Okay, so 36, it is equal to moment of inertia and then times 2 here. So moment of inertia, it is equal to 18 kilogram meter squared. That is the first part of the question here. It says, what is the moment of inertia of the wheel? And we just found it here. The second part of the question says, what is the torque of friction here, right? What is the frictional torque? In order to find the frictional torque, what does frictional torque do to the object, by the way? It is going to slow it down, right? So because it is going to slow it down, so we'll have to use this one. So we can say the frictional torque of friction it is equal to moment of inertia times angular acceleration, yes? So can I write 36 again? No, because this was the net torque, was the combined applied and friction together. It would have been a resulted, or it would have resulted a net torque of 36. But now we're going to find frictional torque, and then frictional torque is going to be different. But since it is the same wheel, isn't it the same wheel? Yes, since it is the same wheel, of course, the moment of inertia, it is a scalar quantity, it doesn't change because the shape of the wheel doesn't change, the radius of the wheel doesn't change. Whether the wheel speed up or slow down, it has the same moment of inertia. And we already found the moment of inertia, which is 18 times. Now, in order, let's say for frictional torque, the frictional torque is what is going to slow down and make it stop, correct? So this is the part that you have to consider. Regarding the angular acceleration, we'll say final minus initial, but what is the final? 0. The initial for the slowing down part, it is 12 divided by what? Divided by 65 seconds, because this is how long it takes. And then we can say frictional torque, it is equal to what? 18 times, or let's do this part first. Negative 12 divided by 65 multiplied by 18, the answer is going to be negative 3.3. Negative 3.3, that is Newton meter. This is the frictional torque. Okay, now that is the second part of the question. The part of the question that was unfamiliar to a lot of students was this part in here. You can add another part. Now you can make part CD. I want to add another part right here. Okay, write another part, or part C, for me right below this question here. So let's go below and make this one part C. The reason why, you might say, why not, find C and then make this part D? No, because this part is related to part A and B here, so we'll have to make it part C here. So write this as a question for yourself. The question would be, what is the torque? What is the torque by the applied force? By the applied what? By the applied force. Okay, now, and you can also write this in an equation as well. If you look at, or look back at the first line, it says the net torque for a combination of the applied force and friction produce a net torque of this. So we can say the net torque, it is equal to, there are two torques by the way, a torque of the applied force and then plus a torque of friction. These two together both produce what? A total of 36 Newton here. Okay? So part C says, what is the torque by the applied force? Don't forget. Now, we already found the torque by the, let's say, the torque of friction here. What was the torque of friction? So the torque of friction was negative 3.3, yeah? Okay, so can you find the torque by the applied force? Yeah, so we can say the torque by the applied force, or you can say the torque applied plus this one here, it is equal to 36 here. So what would be the torque by the applied force? We'll just move this one to the other side and say the torque by the applied force, it is equal to 36. And if we move this negative to the other side, that would be plus, right? Plus 3.3, that is going to be 39.3 Newton meter. This is the question where a lot of students were not paying attention, and because of this, a lot of students got 98, not 100. So always read the question carefully, read in between the lines or whatever says anything. Always make sure what the question wants, all right? Because this question previously been in Wazari a few times, and then all the time they were asking for frictional torque, okay? And then students were not, or a lot of students were not paying attention to this. And the sad thing is this, whenever there's a question like this, you'll always have a wrong answer that is exactly the same as what you just found, for example. So a lot of students thought it was frictional torque, and sadly, the answer that they found for friction was in the choices. So once they saw this, they were thinking like, okay, that's the answer, I got it right, and then unfortunately it was not the right answer. So make sure you add this part to the question, what is the torque by the applied force? Okay, and write this equation as well, because that's what the question says. The net torque, it is equal to the torque by the applied force plus the torque by the friction. These two combined produce a net torque of 36. You already found the frictional torque, and now the applied torque is unknown. You can easily find that one here. Okay, so what is the next part that we have? Now that'll be part D, right? You can consider or make this part D now. Okay, it says how many revolutions does the wheel make during this entire 71-second time travel, let's say. So that is for both speeding up and slowing down. How many times will the tire rotate? See, this is the answer that a lot of students have found, and sadly this answer was in the choices too. Okay, so remember for part C we said the net torque is equal to torque of the applied force plus the torque of friction, 36. It is equal to torque of the applied plus, you can say, or just minus 3.3, makes no difference. The torque applied, 36 plus 3.3, that'd be 39.3 Newton meter. That'd be the answer for part C here. Now it is time to answer part D, right? So how do you do that? It says through how many revolutions does it rotate here? So because we have initial and final, and delta t here as well. So don't forget, angular acceleration is neither given nor required. So which equation do you have to use? Both speeding up and slowing down. You'll have to use the second equation. The second equation says delta theta, it is equal to 1/2 omega initial plus omega final delta t here. Okay, so 1/2 again, initial was 0, final is 12 times 6 here. That is going to be 3 times 12, that is going to be 36. 36 what? Radian. The question says how many revs. I'll just find radian first. Let's call this one delta theta 1, that is for speeding up. Delta theta 2 here, it is equal to the same equation, omega initial plus omega final, and then delta t here. 1/2. What is initial at this point for slowing down? It is 12. Plus final is 0. For how long does it take? This time it takes 65 seconds. Be careful here. So let's find how much is this. That is 65, we can say, times half. And then times 12, we could say. That is 1,560. That is going to be radian. That is delta theta 2 now. If we want to know how many times did it revolve, then we'll have to add these two together and then just convert it. So we can say delta theta total delta theta total, it is equal to delta theta 1 plus delta theta 2. That is 36 plus 1,560. Let's see, what is the total? The answer is 1,596. But this is in radian. How do we convert this into rev? Just divide by 2 pi. Once you convert this one, divide by 2 pi. The answer is going to be 254 revs. This is how many times it got revolved in here. I feel like I've made a mistake. It's 3. That is also true. 5 times 0.5, and then times 12. 390. Oh, this is wrong. This is 390. Okay, if this is 390, please fix this one. Made a calculation mistake. 390. These are going to be different. 390 plus 36. It is 426. 426. 426. 426. Okay, divide by 2 pi. 426 divided by 2 pi. The answer is going to be 67.8 revs. 67.8 revs. This is how many times it revolves during this time interval. So that's this much. There's nothing more than this, but as long as you're careful with the first requirement, or with what was asked, because it could be very misleading. If you're not reading the questions carefully, then of course you're not going to get it right. Now another question here, that would be this. It says a cable passes over a pulley. Here's a pulley. Let's do this one too. What does it say? A cable passes over a pulley that rotates about a fixed axis. And because of friction, the force in the cable is not the same on opposite sides of the pulley. The force on one side is 120 Newton and the force on the other side is 100 Newton. Right? Assuming that the pulley is a uniform disc, don't forget that is also a keyword, with a mass of 2.1 kilogram and a radius of this much, and determine the angular acceleration of the pulley here. So let's draw the shape perhaps. That is a pulley here. There are two forces acting because of friction. The two forces are not equal. One of them is 120, the other one is just 100, okay? That is this. What is the radius of this pulley here? The radius, by the way, for both sides is the same, and it is 0.81 meter. That is the radius. Says find what? Find or determine the angular acceleration here. So, well, we know that the net torque, it is equal to moment of inertia times angular acceleration. So this is unknown. But for the net torque, we know that it is equal to what? Since we have two forces here, each one of these forces producing a torque in here. So this one produces a torque to this side, this one produces a torque to the opposite side here. So we can say force times the radius for one of them minus, because this is how you find the net, because these are in opposite direction, force times the radius. You can call this one F1, R1, because the radius is the same, so we don't have to write R1. This would be F2 times R. It is equal to moment of inertia. Since it says a disk, that is 1/2 mass times radius squared times angular acceleration, which is unknown here. And by the way, you can take the R as a common factor here. That would be F1 minus F2, which is the same thing here. You could just find them. If not, you could just say F1 minus F2 times R, which is the same thing. But at this point, we're just going to do them here. So the first force is 120 times 0. What was the radius? 0.81. That's 1. By the way, big minus small, minus 100 times 0.81. That is equal to 1/2. The mass is 2.1 kilogram times the radius is 0.81 squared times the angular acceleration. All you have to do is just do the math and that's it. It would have been easier if we just did that here. So 120, let me just do this as a matter of fact. 120 minus 100, that would be 20 times 0.81. It is equal to 16.2, we can say. It is equal to. The other side, that is 0.5 times 2.1 times 0.81 squared. It is equal to 0.6889. We can say 0.69 by rounding times angular acceleration. All you have to do is just divide both sides by 0.69. So 16.2 divided by 0.69. The answer is going to be 23.48, we can say by rounding. So angular acceleration. Did I square this one? Yes. Okay, so angular acceleration is going to be 23.5, we can say. That is going to be radian per second squared, and that is the angular acceleration. Easy enough. Once again, if you just know what is given and what is unknown, then the rest will be very easy. 23.5, 24. These are all just fine here. Okay, these are some mosaic questions. You can see these are similar to what we have just solved in here. Okay, now that is a new concept here. That is angular momentum. Now that is also interesting. What is angular momentum? Now, if you remember in grade 11, we had momentum. And what is momentum? Let's say if an object we're moving, certain object we're moving on a surface, like a box, for example. It could be a car in here. They had a certain mass and they had a certain velocity. So we were saying these objects have momentum. What was momentum? Which was the product of mass times velocity. Momentum was a vector, of course, and you can see that the direction of the momentum would be the same as the direction of the velocity here. But this here, because we're dealing with rotational motion here, if an object has a certain mass, if an object, we can say moment of inertia here, and if it is rotating with a certain angular speed, then we can have angular momentum here. So this one, it is called momentum. Okay, and that was grade 11, don't forget. And you can say the unit for this one, it was kilogram meter per second here. Okay, but what about this in grade 12 now? Instead of momentum, we have something called angular momentum. What is it called? Angular momentum. Instead of just calling it momentum, we'll add angular. Because why? Because we're dealing with rotation and angles, you could say. And the symbol for angular momentum, it is capital L here. All right, what is it equal to? Instead of, it's the same equation as this, by the way. Instead of the mass, what do we have? What is the analog, the substitutive mass in rotational motion? It is moment of inertia. Instead of speed or velocity, we have angular speed, right? And that is the equation of angular momentum in rotational motion. Any object that has a certain mass, or you can say moment of inertia, and that is rotating with a certain angular speed, it would always have angular momentum here. Angular momentum is a vector quantity. The direction of the angular momentum would be the same as the direction of the angular speed. What is the unit of angular momentum, by the way? The unit for moment of inertia, that is kilogram meter squared, multiplied by angular speed, it is radian per second. But once again, radian is a dimensionless unit, so once we're combining this, we're just going to cancel out radian. So it is going to be kilogram meter squared divided by the second here. That is also, now we can say this is the unit for angular momentum here. Okay, that is angular momentum. Can I, by the way, how do you define angular momentum? The same way that we used to define momentum. We were saying momentum, it is the product of mass times velocity here. What about this point here? Can I say it is the product of moment of inertia, the multiplication? The product would be best. Of moment of inertia and angular speed? Yes, and that is the definition of angular momentum right here. Of course, for an object, it needs to be rotating as well. So angular momentum, it is the product. And you do know that the product means the answer of two things or something, let's say some things being multiplied here. The product of a rotating object's moment of inertia and angular speed about the same axis. Angular momentum is defined by the following equation. That is the equation. Now this angular momentum, let's not forget, now we said in grade 11, we had translational equilibrium or linear, we had linear momentum, yes? For translational momentum, you could say P, it was mass times velocity, right? These are, of course, were vectors here. But now, what do we have? We have angular momentum, which is moment of inertia times angular speed. So can I say in translational speed, that is what I have? And this would be the analog of momentum in translational speed would be angular momentum? Yes. Right? If not, you could say angular momentum is a vector, or not. You could say the analog of linear momentum, that would be angular momentum in rotational motion. That's it. Angular momentum is a vector quantity and has, or you can say the direction of the angular momentum would be the same as the angular speed, which we just mentioned that. Now, these are the two equations you need to know for both translational and rotational momentum here. Or you can say we call this one momentum, and we call this one angular momentum. But now there is one thing I need you to be aware of, and that is this. We just said that angular momentum, it is equal to moment of inertia times angular speed. Is that true? Yes. Based on this equation, we can see that angular momentum is directly proportional to what? To the moment of inertia. In other words or cases, the larger the moment of inertia, the larger the angular momentum would be. That is first. And also, angular momentum is directly proportional to angular speed as well. The larger the angular speed, the larger the angular momentum. But then there is one thing you need to be aware of. What about if I make one of these the subject here? Moment of inertia would be, or it is equal to, angular momentum divided by angular speed in here. So now we know that if anything above the fraction is directly proportional, anything below is inversely proportional, right? So based on this, we can say moment of inertia is inversely proportional with what? With angular speed. Now, do you remember so far we've been saying that if the moment of inertia of an object is large, then the angular speed would be small, or it would be smaller because these are inversely proportional. Now, all what we were saying it is basically coming from this equation right here. But we just did not have the equation up to this point, but now we have the equation. So once again, what is the relation between moment of inertia and angular speed? These are inversely proportional. Once again, if the moment of inertia of an object is larger than the angular speed is small, and vice versa. If I can make the omega as a subject as well, that would be 1 over moment of inertia. So you can see that if we increase this one, this decrease. If we decrease this one, of course, this one is increased because these are inversely proportional. This is also something very important you need to be aware of. Now, there is also something very important, says angular momentum may be conserved. And now we have the law of conservation of angular momentum, which is something very important you need to know. We can say that angular momentum is conserved, but remember there's a condition for angular momentum to be conserved, okay? What is the condition? The net torque or the net external torque acting on the object must be 0. In other cases, or in other words, we can say if the net external torque acting on an object is 0, then the angular momentum remains the same, remains conserved. If it stays the same, now we can say it is conserved. So I need you to underline this for me here, because this would help you a lot for later uses. The law of conservation of angular momentum states that, or it is, when the net external torque acting on an object is 0. So if the net external torque acting, let's say external though, net external torque acting on an object is 0, then we can say the angular momentum is conserved. What do I mean by the angular momentum is conserved or stays the same? That means angular momentum before and after will be the same here. Initial, final, before, after will be the same, and that is what exactly the law of conservation of angular momentum represents in here. Okay, so once again, what is the law of conservation of angular momentum? When the net external torque acting on an object is 0, then the angular momentum remains the same. It does not change. It is conserved. All these are the same thing. Now, what are the equations that we have related to the conservation of angular momentum? If we can say, if the net external torque, if the net external torque acting on an object is 0, then we can say angular momentum is conserved. If that is the case, we can say angular momentum initial would be the same as angular momentum final. But what is angular momentum initial equal to? It is equal to moment of inertia times angular speed. These are both initial, we could say. It is equal to moment of inertia of the object times omega final here. Let's make this one final. In other words here, these are, or this would be the same, but sometimes we have more than one object. If we have more than one object, what would happen? We can say moment of inertia of object number 1 plus angular momentum of object 1 plus angular momentum of object 2, these are both initial, would be equal to moment of inertia angular, wow. I think it's This is getting late, perhaps, maybe. So angular momentum of object 1 plus angular momentum of object 2, these are both final. This would be the same. And once again, each one of these, of course, would become moment of inertia, angular speed. That would be for object 1, moment of inertia for object 2, whatever. Then, of course, it will expand a little. So let me just do this one more time. But then, don't worry about this if it is getting too much. I'll just tell you what exactly you need, and that'll be it in here. But I'll just do that so that you have an idea. What is the moment of inertia of object 1 equal to? That'll be moment of inertia times angular speed. These are, you can say, for object 1 plus, let's say, that'll be moment of inertia object 2, angular speed object 2. These are all initial, don't forget. It is equal to, we can say I omega plus I omega. Let's just make it quick. And then these are final. This is object 1, object 1, object 2, object 2. So this is what it is. So this side here must be equal to the other side. But what exactly do you need to know at this point? The question will always ask for what is, all the questions that we have, they'll ask what is omega final of the object in here. By the way, let me tell you this. If an object or two object is rotating, let's say there's a merry-go, something like a disc that rotates here. If an object is resting, or let's just say if an object is in this merry-go, no matter how fast or slow the merry-go is rotating, isn't it that the angular speed of this object would be the same as the angular speed of the merry-go? Yes, right? Well, thank you for saying that. But now I'll just make these the subject if that is the case in here. So instead of doing all this, I'll say moment of inertia of object 1 plus moment of inertia of object 2. I'll just write 1 omega, right? And these are both initial, because these two objects would be moving the same. And then as for the final here, like let's say the merry-go, it is rotating at a certain speed. Then after that, it is speeding up or slowing down. Like, doesn't matter if it is speeding up or slowing down, whatever the speed of the merry-go is, the speed of this object will be the same as the merry-go. So we can say moment of inertia of object 1, moment of inertia of object 2 would be final times omega final, right? That's what it is. So their angular speeds will always be the same, whether if it is speeding up or slowing down. So what exactly do you need to know? The only thing you need to know regarding the conservation of angular momentum is this equation right here. So we can say, the question says, I should have brought this one here. The question says, wow, that's unfortunate. The question says, find the final angular speed in here. So this is the equation that I was just writing here. Moment of inertia of object 1 of object 2. Initial angular speed, it is equal to moment of inertia of object 1 of object 2. These are final angular speed final, yes? The question says, all the questions that we have, they'll ask for omega final. So how do you make omega final in this equation? We'll say omega final, and that is the only equation you need to know, by the way. It is equal to moment of inertia of object 1 plus moment of inertia of object 2, initial times omega initial, over moment of inertia of object 1, object 2, these are final here. That is the only equation you need to memorize. And of course, beside this, let me just write this one as well. So we have to say initial angular momentum must equal to final angular momentum. If you have two objects, you could just say this. 1 and 2, these are both initial. 1 and 2, these are both final. If you have two objects. If you have one object, you could just say initial that is equal to final. So that is the main equation that you need to know, because this one tells you that the angular momentum is conserved. If it is conserved, if you have two objects, if you have one object, that is this. If you have two objects, that would be this. Then you immediately jump right into this question here. So whatever that is unknown, you will find it, and that's it. Later, I'll explain more what exactly you need to do at this point here. But for now, when the angular momentum is conserved, all the questions that we have, it require only this equation here. So just remember, omega final, it is equal to moment of inertia of object 1 and 2, over 1 and 2. This would be times omega initial. Here would be omega final, by the way, but we just brought omega final from here to there so that it no longer at this point, and that's it. Okay. Wow, I think that was too much. But now let's move on and see what is next. So you can see that these are all what we have. There's one more thing perhaps. If the question ever want to mix or combine these two together, you can use this equation as well. That'd be, where does this come from, by the way? That is, if we have one object, you can say moment of inertia of object, let's say times angular speed, these are initial. It is equal to moment of inertia final, omega final, yes? So that is for one object, don't forget, okay? So if you need or ever need any of those, of course, you can make this as an equation here. But since we have omega final over omega initial here, so this is how it goes. It depends on what the question, if they ever ask for it, even though we don't have any question that can ask for this, but just in case, Yani, we move this one here, so this one would move at this point here. There is this way that can help as well. Initial has to be with initial in the same line, and final has to be with final on the same line at this point here. And this is the equation that I told you need the most, and that'll be this. Now we have something, how does the law of conservation of angular momentum applies to an ice skater here? Watch this. Now, you've seen ice skaters. Hopefully we can, if we have the chance, we'll watch this one, inshallah. We'll watch a video to see just how it is. Let's say if a person is standing here, their hands are close, let's say, to their body, especially if they're rotating here, don't forget. If they have a certain angular momentum, because they have moment of inertia, and they have angular speed because of the rotation, so they have angular momentum. If no external torque is acting on the person, remember this. That means if there is no second person involved making the person spin faster or slower, we can say the angular momentum is conserved. And if that happens, watch what is next, right? So if the person extends their arm, then of course the mass would be far from the axis of rotation, right? If the mass is far, what do you think will happen to the moment of inertia? It will decrease, right? If moment of inertia decreases, what do you think will happen to the angular speed? Then we say these are inversely proportional. So watch this. Angular momentum, we said it is moment of inertia times angular speed. If angular momentum is conserved, yani constant, it doesn't change, it remains the same, right? Okay, so if the arms are extended, watch this. If the arms are extended, then can I say the moment of inertia increases? Why? Because the mass, of course, now it is moving far from the axis of rotation here. True? That is for both sides, of course. If moment of inertia increases, then angular speed decreases, so the ice skater's spinning will slow down. That's been in Uzari many times. But what if the person brings their arm and feet closer to the axis of rotation, closer to the center of their body? Then, now once they bring in, the mass would get closer to the axis of rotation, yes? If the mass gets closer, that means moment of inertia decreases, then angular speed must increase, so the person must spin faster. That is what you need to know. Regarding the angular momentum, it must remain the same because there is no second person involved, or you can, if we assume there's no friction too, by the way. So this table is very important. Make sure you know this. When the hands and feet are far from the body, remember this. Moment of inertia, we said increase because the mass is far from the axis of rotation. That is first. If moment of inertia increases, then angular speed decreases. All right? Then angular speed decreases, so L remains constant. But as a result of this, then the spinning will slow down here. But what happened when the mass is brought close, let's say back close to the axis of rotation, both hands and feet are closer to the axis of rotation, then we can say moment of inertia decreases because the mass is closer. True? If moment of inertia decreases, angular speed increases. Can I say the person is going to spin faster now? Yes, because L is constant, and that is what it is. So don't forget, if the net torque is zero, if there's no friction, then the angular momentum is conserved. I'll repeat this for the last time. If you extend the arms and the leg, so the mass will be far from the axis of rotation, moment of inertia increases, angular speed decreases, the person's rotation will slow down. But when they bring the arms and leg closer to the axis of rotation, the mass will get closer to the axis of rotation, then moment of inertia decreases. As a result of that, angular speed increases because they are inversely proportional, and then the person start to spin or rotate faster. And then because the angular speed, the angular momentum will be conserved at that point. Let's see if we can watch this. All right, let's take a look at this. Okay, I want to watch this two here. The first one that we have is this. Look at this person. First of all, the arms were extended, it was slow, but as they bring their arm in, you can see that it is going to spin faster here. See, the arms are extended again, so this spinning slows down here. All right, another video here. You can also see that from here as well. Let's just pause this one maybe. Take a look. If the arms and leg are far, so slow rotation, but as she brings them in, you can see that the rotation becomes faster. All right, we also have this one, which is also very interesting here. So you can see that there's this mass, I don't know what shape is this, but once, for example, left alone, you can see that the mass is far from the axis of rotation, so slow rotation, but as you pull the string, it brings the mass closer. You can see how fast it spins at this point here. So this is all about the conservation of angular momentum. Okay, and once again, in each one of these cases, of course, the angular momentum is conserved. All right, now moving to the next question here. What does it say? It says, what happens? These are questions, by the way, these are very important too. I need you to pay attention to them. It says, what happens when an ice skater brings his hand and feet closer to his body? So that once they bring their hands and feet closer to their body, the mass gets closer, right? So the moment of inertia would be less or decreases, angular speed increases, so the person spins faster. That's the first thing. All right, second, or question 24 says, is angular momentum always conserved? Now go back to the definition of the law of conservation of angular momentum and tell me what you've underlined, right? It says the angular momentum is only conserved when the net external torque acting on the object is 0. Then it will be conserved. If not, it is not conserved. Question 25 is also very important, says, is it possible for two objects with the same mass and same rotational speed to have different values of angular momentum? This one is a bit tricky, and if you're not careful, of course, you can easily fall for this one here. So the answer to this question is yes, it is possible to have different angular momentum. Does it say different what? Different angular momentum? The answer would be yes. And why is that? Let's take a look at this. What does the question say? It says, is it possible for two objects with the same mass and rotational speed to have different values of angular momentum? Yes. So first of all, let's see what is the angular momentum equal to. Is equal to moment of inertia times angular speed. Is that true? Now let's break this one down. If you're not careful, you might say just the same mass and same angular speed. You might just say if these two are equal, then of course they must have the same angular momentum. That might be your first answer response to this, but that would be incorrect. Why? Because, watch this, if I break this one further down, for moment of inertia, it is equal to a constant, a number times mass times radius squared, and then times angular speed. So the question now says, for two objects that have the same angular speed and mass, is it possible to have different angular momentum? The answer is yes. It is true that they have the same mass and angular speed, but what if they have different radiuses? right? What if they have different shapes, for example, or different mass distribution, right? So of course, well, just because these two are the same does not mean their angular speed will also be the same. No, because if any of these values were different, the radius, the shape we can say, or the mass distribution, then of course their angular momentum would be different. And that is the answer to the question. It says, is it possible for two objects with the same mass and angular speed to have different values of angular momentum? The answer is yes. Okay, because in order to have the same angular momentum, they must have the same angular speed, the same mass, the same radius, the same shape, the same mass distribution, and everything. Then we can say then of course they would have the same angular speed. So the answer to this, it is yes, they can have different angular speed depending on both, let's say it depends, angular momentum depends on both rotational speed and object's moment of inertia, not just mass. So therefore, any two objects with equal masses and rotational speed, but watch this, with different shapes, may have different angular values here, or different angular momentum values here. And this is the hint or the note, like for them to be equal, all of these must be equal here. So they must both share identical values for mass, radius, and omega, including the same shape. Then or any alteration, any changes, it means, to these values will result in a change in angular momentum. Okay. Now it says a child on a merry-go moves from the near the axis to the outer edge on the merry-go-round. What happens to the rotational speed of the merry-go-round? Explain this. Okay. So let me tell you regarding this one a little. Watch this. There is a merry-go, just like the one that you saw in a diagram here. Like a disc, here's the axis of rotation. If a child moves from near the axis to the outer edge, or vice versa, watch this. Do you remember the ice skating? We said when the person extends their arm, the mass would be far from the axis of rotation, yes or no? If the mass is far, the angular or the moment of inertia increases, angular speed decreases, right? So watch this. If a person moves from near the center to the outer edge, do you think the mass gets closer to the axis or away from the axis? The mass would be away from the axis, right? So the mass would be away. The mass moves away, let's say. The mass moves away. If the mass moves away from the axis of rotation, then moment of inertia increases. If moment of inertia increases, that makes the angular speed of the merry-go to decrease. As a result of this, we can say the merry-go slows down. But what happens if it is the opposite? A child is close to the edge. At this point, it is walking towards the center. If it is walking towards the center, let's say moving away from the center, at any point, if it is walking or moving towards the center, you can write this as a note here. Then, of course, moment of inertia decreases, angular speed increases. As a result of this, we can say the merry-go, whatever the object that is rotating, it is going to speed up, right? Of course, it applied to the ice skater too. So remember this note, and of course, this can help you to answer any question related to this one, whether if it is moving closer to the edge or let's say moving away from the axis of rotation or moving closer to the axis of rotation. So the angular speed decreases because the moment of inertia increases. The decrease in angular speed makes up for the increase in the moment of inertia. By the way, because there's no third person involved in here, so the angular momentum is conserved. The last question for today, that is 27, says, is it possible for an ice skater to change her rotational speed without any external torque? Explain your answer. The answer is yes. We said by extending their arms and legs outward, the mass would be far from the axis of rotation, the moment of inertia increase, the angular speed decrease. We could do the opposite too. By bringing the arm and feet closer to the axis of rotation, the moment of inertia decrease, angular speed increases. So this is how we can do that without any second person involved, which you can call it the external network at this point. So that'll be the end for this session. I hope you understood this. If not, just go back to the beginning and then rewatch this one, and feel free to reach out if you have any questions. Till then, keep practicing, and I'll see you soon, inshallah. Assalamu alaikum wa rahmatullah.